thermodynamics, second law. Second law of thermodynamics, that related problem. An inventor claims to have developed an engine that during a certain time interval takes 110 megajoule of heat at 415 Kelvin, rejects 50 megajoule of heat at 212 Kelvin, while manages to do 16.7 kilowatt hour work. So this is the work, and total, this is the total heat, 110 megajoule. This is kilowatt hour. That means work done, that is equals to 16.7 kilowatt hour. This is nothing but 16.7 into 3.6 megajoule it is. Megajoule. So megajoule, that means kilowatt hour. 1 kilowatt hour, that is 1 kilowatt hour, 10 power 3 watt hour, 3600 joule it is. So this is right at 3.6 megajoule. 3.6 into 10 power 6 joule, that is 3.6 megajoule. So this is the total work done. Efficiency of the climb. Inventor climbs efficiency of climbs. So that climbs efficiency is W upon Q1 it is. This is W write as 3.6 into 16.7 megajoule upon 110 megajoule. The efficiency becomes, this is right, simplified. So this value approximately, this is 48, this is 55. 55 by 110. So this value, so this is around point, total simplification 0.55. That means efficiency in the percentage, a total, this value after calculation, this value is, efficiency is 55%. Efficiency becomes 55%. This is climb's efficiency. But initially they given the temperature and T1 and T2. T2 rejected heat 50 megajoule. This is Q2. This is nothing but T2. This is nothing but T1, initial heat related temperature. The efficiency due to the theoretical part, the theoretical efficiency is right as 1 minus T2 upon T1. Its value became theoretical efficiency. It is theoretical efficiency. This is climbs, efficiency in climbs. This is MC, 55%. Theoretical efficiency, this is 212 upon 415. Its value becomes 203. So this is nothing but 203 upon 415. This value, efficiency in theoretical, this simplification, its value equals to 0.49. So this is theoretical efficiency it is. And the percentage of theoretical efficiency is 49%. Theoretical efficiency 49%. Climbs that efficiency 55%. Do you agree with the inverted climbs? So originally it is, the efficiency is 49. Efficiency becomes 49. So this is the giving efficiency. An inverter claims to have developed an engine that during a certain time of interval takes like this. That means claims efficiency is greater than theoretical efficiency. So theoretical efficiency से compare किया तो claims efficiency is so greater, but theoretical efficiency is lesser than. So do you agree? Why we are agree? So why we are agree? This value is less. That means this value is less, we do not agree to climbs. So do not agree to climb, okay, to take the, so inverted, do not agree to climb. Okay, this is the theoretical efficiency is less, so we do not agree to climb that inverter. So do not agree to climb that inverter. An automobile engine absorbs 1600 joule from a hot reservoir. So this is engine absorbs, this is the heat. So reservoir and expels 1000 joule to a cold reservoir of a cycle. So that means Q1, that value becomes 1600 joule, and Q2, that is nothing but 1000 joule. Q1 and Q2. So what maximum work done in each cycle? Work done. So first question is what maximum work done? Maximum work W is right as hot reservoir minus cold reservoir. This is 1600 joule minus 1000 joule. Then work done becomes 600 joule. Work done becomes 600 joule. And the second one, what is the efficiency? Efficiency right as W upon Q1. It is right as 600 upon 1600. So this is right as 3 upon 8. 0 point. So its value 375 efficiency and percentage. So eta equals to 37.5%. This is the efficiency. Again, C it is. C right as third problem. What is the efficiency of the cycle? And third one, this is the second one. Okay, what is the efficiency? And third one is what is the power output of engine operates 200 cycle per minute. That means here the frequency right as 200 per minute per 60. This is the frequency. We want time period T equals to 60 by 200. Its value equals to 0.3 seconds. This is the time period. We want what is the power output. Power is right as work upon time. This is the power. Work is nothing but 600 joule upon 0.3. This is right as 6000 by 3, 2000 watt. This is the power output. It is. The temperatures T1 and T2, two heat reservoirs in an ideal Carnot engines, two reservoirs it is 1500 degrees centigrade and 500 degrees centigrade respectively. Which of these the increasing T1 by 100 degrees centigrade or decreasing T2 by 100 degrees centigrade? What result in the greater improvement in the efficiency of the engine? Efficiency we want, first efficiency. Suppose this is T1, this is T2. T1 1500, T2 500. This is hot body temperature, cold body temperature. First case, which of these increasing T1 by 100? So you know that 1 minus T2 upon T1. Otherwise, eta equals to 1 minus T cold upon T hot. Like this is the relation. So initially, this value. So compulsory T1, T2 in Kelvin. T1 becomes 1500 plus 273. 1773. And T2 500 plus 273. Its value becomes so 773 Kelvin it is. T1 and T2 value. T1 increasing by 100. T1 increases by 100 degrees centigrade. Then efficiency in first case T1 increasing by 100 degrees centigrade. So this condition efficiency eta equals to 1 minus. So this is T2 775 upon 1773 plus 100, that is 1873 Kelvin. Increases by degree centigrade and increases by Kelvin, same value. Degree centigrade and Kelvin, its value becomes same. 1875 minus 1773. So 1873 minus 773. It is nothing but 1173 upon 1873. 1173 upon 1873. This is T1 increases by 100 degrees centigrade. Its value approximately 1873 upon, so this is 1000, so 1173 by 1873. Its value becomes 0.6, it is 0.6, 1173, 1873. So its value becomes 24, 18, 143, 4, 48, 52. So 62% approximately. It is 0.62 efficiency. And suppose T2 decreasing by 100 degrees centigrade. Decreasing by 100 degrees centigrade, that means T2 decreases by 100 degrees centigrade. Efficiency eta to 1 minus. So this is decreases by 100, 673 upon this value becomes 1773. T1 no change. Its value becomes 1773 minus 673. It is nothing but 1173 upon 1773. Its value becomes 1773. This is 6 times. So 6. %68%. So its value around 0.66. That means eta 1 is 62%. Eta 2 becomes 66%. That means temperature increases of hot body temperature increases, efficiency is 62%. Cold body temperature decreases, efficiency is 66%. Efficiency increases when decreasing the cold body temperature. If the cold body temperature T2 becomes 0, this condition efficiency becomes 100%. Heat engine efficiency becomes 100%. It is. Cold body temperature becomes 0. If cold body temperature 0, efficiency of heat engine is 100%. Total heat converted into work form. Efficiency becomes 100%. It is. And again, the second question is given here. A hot heat engine has efficiency 1/6 part. 1/6. Efficiency of heat engine 1/6. When the efficiency becomes, this is N1, efficiency becomes N2 1/3. When the temperature of sink decreases by 100 Kelvin. Already you know, temperature of sink decreases. Efficiency increases. Temperature decreases, efficiency increases. Where this is, so here efficiency becomes 0.166. This is 0.33. Efficiency increases it is. So temperature of sink decreases by T1, temperature of source. So temperature of source it is. T2, temperature of sink. Temperature of sink it is. So sink temperature decreases to 100 Kelvin. Temperature of sink decreases to 100 Kelvin. Then efficiency, here the efficiency equals to N2 equals to 1 by 3. So initially the efficiency is 0.16, matlab 1 by 6. But present the efficiency is temperature of sink decreases, then efficiency is 1 by 3. So initially N1 is brighter, 1 minus T1 upon T2. This is 1 by 6, that is equals to 1 minus T1 upon T2. Its value T1 upon T2. This value equals to 1 minus, T2 by T1. T2 upon T1. So it is T2 upon T1. Cold body temperature by hot temperature. T2 by T1. Its value becomes 1 minus 1 by 6. This is 5 upon 6. So this is initial condition. This is the T2 by T1. After eta 2, this is equals to 1 minus T2 minus 100 by T1. T2 minus 100 by T1. This case the efficiency is 1 upon 3. 1 minus T2 minus 100 by T1. T2 minus 100 by T1. Its value becomes 1 minus 1 by 3. 1 minus 1 by 3 it is nothing but 2 by 3 it is. 1 minus 1 by 3, that value nothing but 2 upon 3. You know that T2 upon T1 minus 100 by T1, this is equals to 2 upon 3. T2 by T1, that is equals to 5 upon 6. This is write as 5 upon 6. 5 by 6 minus 100 by T1, that is equals to 2 by 3. Its value 5 by 6 minus 2 by 3 equals to 100 upon T1. Its value becomes 4 upon 6, that means 1 by 6, that is equals to 100 by T1. Where T1 equals to 600, T1 equals to 600 Kelvin. T1 that is equals to 600 Kelvin. Then what about the T2 value? T2 value is T1 by T2, that is 5 by 6. Then it is T2 equals to 5 by 6 into T1, that is 600. Its value T2 equals to 500. This is the T2 value. That means temperature of the sink, that value equals to 500. And integral number of complete cycle. So integral number of complete cycle. A reversible engine absorbs 1200 joule from the reservoir at 400 Kelvin and performs 200 joule of mechanical work. So mechanical work is 200 joule of work. Find the quantities of the heat exchanged with the other two reservoirs. Other two reservoirs, suppose this is Q1 equals to 1200 joule. Then work done equals to 200 joule. Then what is Q2 and Q3 value? Q2 and Q3 values. Conservation of energy. What is the relation? Conservation of energy. The total heat Q1 is equals to W plus Q2 plus Q3. Its value 1200. This is equals to 200 plus Q2 plus Q3 it is. The final relation is Q2 plus Q3, that is equals to 1000 it is. Q2 plus Q3 equals to 1000. And another condition, here in reversible process entropy becomes 0. The sum of entropy of the total system, sum of entropy of the system becomes 0 means entropy write as Q1 by T1 plus Q2 upon T2 plus Q3 upon T3, its value becomes 0. Reversible process. So reversible process, the sum of entropy becomes 0 it is. Sum of entropy becomes 0. This is providing 1200. That means minus 1200 upon. So temperature 400. It is plus Q2. Q2 upon 300 it is. Plus Q3 upon 200. These values are simplified. This value becomes 0. So it is minus 300. So its value becomes minus 300 plus Q2 by 3 plus Q3 upon 2. Its value becomes 0. Then Q2 by 3 plus Q2 by 3. Q2 upon 3 plus Q3 upon 2. Its value becomes 300. After simplification, this is 2Q2, 2Q2, 3Q3. Its value equals to 1800. To multiply it by 6. So this is another equation. First one equation is, this is Q2 plus Q3 is 1000 and 2Q2 plus 3Q3 equals to 1800. So this value Q2 plus Q3, this is 1000, where Q2 write as. So Q2, so in this problem, this is write as the continuation of the problem. Q2 plus Q3, this is 1000, where Q3, 1000 minus Q2. So this value put here 2Q2 plus 3Q3, write as 1000 minus Q2. Its value equals to 1800. 2Q2 plus 3000 minus 3Q2. Its value equals to 1800. Then this value is minus Q2 is equals to, this is minus 1200 it is. Minus 1200, this value equals to Q2 becomes 1200. Q2 becomes 1200. And what about Q3? Q3 value. So this is Q2 plus Q3, that is equals to 1000. So Q2 plus 1200, that is equals to 1000. Where Q3 plus 1200, that is equals to, where Q3 equals to 1000 minus 1200, its value minus 200 joule. That means this is Q3 value. Q3, Q2, this is the condition. Find the quantities of heat exchanged. Find the quantities of heat exchanged. Using these two equations, we simplified the Q2 and Q3 value. Q2 value and Q3 value we calculated. Q2 and Q3. So this is a Carnot engine whose sink at 300 Kelvin. T2, that is at 300 Kelvin. The efficiency of 40%. Efficiency becomes 40%. Eta equals to 1 minus T2 upon T1. Temperature of sink by temperature of source. This is 40%. 40 by 100 equals to 1 minus T2 upon T1. Its value becomes 0.4. 0.4, that is equals to 1 minus 300 by T1. 300 upon T1 equals to, this is point, so this is 6. Where T1 equals to 300 by 0.6, its value becomes 500 Kelvin. So that is the T1, initial temperature. That means temperature of source T1, that is equals to 500 Kelvin. If this is the source temperature, the temperature of the source increased to, increased to some certain temperature. This value increased to certain value, T1 plus X. Increased to X, that means T1 plus X. then the efficiency increases its efficiency by 50% of original value. Original value by 50%. Original value efficiency is 0.4. So 50%. New efficiency is 0.4. That means eta plus 50% eta by 2. That means 0.4 plus 0.4 by 2. So 50% means a half of value. This is 0.6 new efficiency. Then new efficiency 1 minus T2 upon T1 plus x. Its value new efficiency 0.6 equals to 1 minus T2. T2 is right as the T2 value. This value is 300 Kelvin. Sink temperature no change. T1 that is 500 plus x it is. So its value becomes 300 upon 500 plus x equals to 0.4. Again its value 500 cross multiplication 300 by 0.4, this is equals to 500 plus x. Its value 500 plus x, that is equals to 750, where x equals to 750 by minus 500, x equals to 250 Kelvin. The temperature increases by 250 Kelvin. Temperature increases by 250 Kelvin. The efficiency 50% increases. Efficiency increases by 50 Kelvin. An ideal gas found to obey the law P square V equals to constant. P square V equals to constant. The initial temperature and volume T naught V naught. If the gas expands a volume to V naught, final temperature becomes. It is an ideal gas, then it is obey the rule P into V equals to nRT, where P is right as nRT upon V. This value using here, so this is P square nRT upon V whole square into V equals to constant. Then this relation is T square upon V square into V, this is equals to constant. So its value becomes T square upon V equals to constant, and T1 square upon V1 equals to T1 square upon V1, that is equals to T2 square upon V2. Initially the temperature and volume. Initial temperature T naught, volume becomes V naught. This is equals to final temperature T2 square. Volume becomes 2V naught. 2V naught, this is the volume. After simplification, T2 square, that is equals to 2T naught square, where T2 equals to root 2 into temperature. T2 equals to root 2 into T naught. This is the temperature. And another, an ideal gas undergoes a pre-process which the pressure is P and volume is P. Obeys the law P power x into V, this is equals to constant. We want bulk modulus. What is the value of bulk modulus? K equals to delta P upon minus delta V by V. This is the bulk modulus. So elasticity concept using Young's modulus, bulk modulus and rigidity modulus. But this is bulk modulus. K equals to delta P upon minus delta V by V. But we want this value, bulk modulus value we want. Differentiation on both sides, differentiation P power x into V, that is equals to differentiation of constant. Its value becomes a differentiation of P power x. P power x, the differentiation of U into V. This method U into dV plus V into du. Using this method, differentiation of U and V. So this method, it is right as differentiation of constant differentiation 0. 0 equals to differentiation of P power x into, this is dV, or nothing but delta V. This is plus. So this is V into differentiation of p power x. Differentiation of p power x, x into p power x minus 1, n x power n minus 1 into dp, that is nothing but delta p. This is the equation, p power x into delta v plus v into x into p power x into p power x minus 1 into dp. This value is simplified here, so these values are simplified. So this is 0 equals to p power x delta v plus v into x into p power x upon p power minus 1, that is p power 1 into delta p. So this is also p power x 0. So cancel here. So after this is delta v it is. So 0 equals to delta v plus it is write as v into x upon p into delta p. X upon p into delta p. Just change these terms. So change this term is changes this side. So that value becomes minus delta v equals to v into x upon p into delta. This v also changes minus delta v by v, that is equals to x by p into delta. This is one term and this is one term. We want bulk modulus delta p upon, this is volume strain delta p. So bulk modulus k equals to, this is pressure upon, this is change in pressure upon, this is volume strain. Volume strain is minus delta v by. So it is right as, so this term is changes this side, p upon x, that is equals to delta p upon minus delta v upon v. This is volume strain. This is nothing but bulk modulus k. K equals to p upon x. So this is bulk modulus. K equals to p upon